Hello, Martin here, and welcome to week 8 of the Calculus 6. This week has a focus on topics that didn't come up on Edexcel Paper 1 2024, but even if you're doing this, looking at this video after that exam has come out, or you're doing a different exam spec, these problems are still going to be really good ones for you to have a go at. So, speaking of having a go, pause the video here and have a go at the problems, and the solutions will follow shortly. Now, to begin with, we're going to look at some parametric differentiation. Now, on paper 1, there were no parametric equation questions, so I very much would think that it would come up on paper 2. And it's very likely you're going to get at least one type of calculus problem with the parametric equations. So in this problem, we've got a curve that is defined by the parametric equations that you can see there. And we're going to find the gradient of the curve when y equals 8. Now, it might be tempting to find the Cartesian equation of the curve and then do dy by dx. And by Cartesian equation, I mean an equation just involving the y's and x's. But it's going to be much easier to use this rule that to find dy by dx, I do dy by dt divided by dx by dt. Okay, so you're going to do two differentiations here and then divide one by the other, but that is going to be much quicker than if you find the Cartesian here and then differentiate that. So that's not in your formula book, by the way, so you do need to remember that one. So I need to find dx by dt in this. So to help me do that, I'm going to write that as t plus 1 to the minus 1. Then what I can do is go to our good old friend, the chain rule. I've been watching these videos for the last 8 weeks. I think I've mentioned the chain rule from time to time. So I'm going to let u be the bit in bracket. Dx by du, well, that's just minus u to the minus 2. Du by dt, well, that's just differentiating t with respect to t, that's just 1. And then when you differentiate the 1, that goes. So dx by dt, we just multiply minus u to the minus 2 times the 1. So it's just minus u to the minus 2, where that u is that t plus 1. Again, probably by this stage you have got a quicker way of doing it, but I just always like to show those steps with the chain rule if you are ever unsure. It's just always a good thing to rely back on. Dy by dt now, we're going to find that. That's going to be a lot easier to do. We're just going to differentiate t cubed with respect to t, multiply by the power, take 1 off the power, 3t squared. So I mentioned that formula earlier, okay? Dy by dx is dy by dt over dx by dt. So let's put these two bits together. So dy by dx is going to be dy by dt, so that's 3t squared. And I'm going to divide that by minus t plus 1 to the minus 2. That's my dx by dt. And then I want to find the gradient when y equals 8. So I've got my gradient function here, but the issue is it's in terms of t instead of y. So what I want to do is I want to find the t value when y is 8. So what I would just do here is just simply look at the parametric equation here, y equals t cubed. So I'm going to look at what the value of t is when y is 8. So 8 would equal t cubed. Cube root of 8 is just 2. So what I need to do is sub in t equals 2. So let's do that. Sub in our t equals 2. Note that I didn't bother to simplify this dy by dx here because I'm just going to sub in anyway. No need to give myself some extra work that I need to do. And when I work that out, I get minus 4 over 3. So I can't stress enough, if there's any sort of calculus surrounding parametric equations where you're going to need to do some differentiation, please don't forget that rule that dy by dx is dy by dt divided by dx by dt. Not in the formula book. You need to remember that one. Okay, let's look at this next problem then. I probably got a little bit carried away with adding an extra bit and another extra bit to this problem as I went along. But let's look at the problem. The curve C has the equation, as you can see there, and we're going to find the coordinates of where the two tangents to the curve at x equals 1 meet. I probably could have just stopped this question at find dy by dx, but I wanted to go further. I wanted to try and think of what could they do in an exam that's maybe a little bit more than just find a gradient. Okay, because we do need to be prepared for that. So we're going to need to, as I mentioned, we're talking about tangents here. So we are going to need to find dy by dx. We're going to need to find our gradient function here. So I'm going to need to differentiate this. Now, it's not possible to make x the subject easily or y the subject easily. So I'm not going to simply just get y equals some function of x and do dy by dx here. I'm going to need to use implicit differentiation. So implicit differentiation, that's where you go to when you can't make either y or x the subject easily. Then you need to use implicit differentiation. So a little reminder how implicit differentiation works. We just go term by term, and if the term is an x, as the first one is here, we just differentiate that normally, okay? So we're just going along differentiating with respect to x here. So differentiate x squared with respect to x, that's 2x. But then your second term's a y. So what we're going to do is we're going to differentiate this with respect to y, which will be 6y. But because I've differentiated with respect to y, to compensate for that, I need to times by a dy by dx. Now you want to be really careful with this third term, 6xy. This catches a lot of people out. Okay, we have a function of x times a function of y here. So you need to be really careful here when you deal with this. Okay, so because it's a function times a function, you need to use the product rule here. Okay, and I think I'm right in saying that product rule didn't come up on paper 1, so do be prepared for that for paper 2. So I'm going to call u the minus 6x, and I'm going to call v the y. You can just do u equals x. You don't actually have to make it minus 6x. You could work this out and times it all by minus 6 at the end. I'm just going to do minus 6 here, and then I don't have to worry about the negative symbol in a minute. So I'm going to do du by dx, which is minus 6, and I'm going to do dv by dx. So I'm going to differentiate y with respect to y, which would just give me 1, but because I've differentiated with respect to y, okay, still doing implicit here again, because I've differentiated y with respect to y, that's 1. I need to times that by dy by dx. Okay, so I differentiate y with respect to x here. I differentiate with respect to y, that becomes 1 times by dy by dx. So then you can use the product rule. So we do u times dv by dx, that'd be minus 6x dy by dx. And then we're going to do du by dx times by v. That's going to be minus 6y. Don't forget about this last bit, okay? On the right-hand side, you've got a 10. We differentiate the 10, that becomes 0. You still need to have this as an equation here, okay? Don't lose that equal sign along the way, as I do often see. So we've got here, we've differentiated, however, we want to get dy by dx to find what our tangent's going to be. So we're going to group together the dy by dx's. And then I'm going to take anything that's not a dy by dx over to the other side. By doing that, what I can then do is divide both sides by 6y minus 6x. Now, I want to find the coordinates of where the two tangents to the curve at x equals 1 meet. Okay, so there's actually going to be, this isn't a function here. Okay, this equation here. Okay, this would be a, it's going to be a many-to-many function. So there will actually be more than one place where x is 1 here. Okay, or sorry, different values for where x equals 1. So what I need to do is find out the corresponding values of y. Okay, so to do that, I'm going to have to go, we're going to do this to the side here. When I substitute in x equals 1 into the original equation, so 1 squared is 1, 3y squared. When x is 1, that's going to become minus 6y equals 10. We get this quadratic. To make that simpler, I can divide both sides by 3. Thankfully, I picked something that would factorise nicely. I'm nice to you guys like that. You might not think it when you're actually doing this pretty long problem. So you get y equals 3 and y equals minus 1. So now we've got two places where x is going to equal 1 here. You've got different values of y. So firstly, I'm going to find the gradient when x is 1 and y is 3. So if I sub that into 6y minus 2x over 6y minus 6x, so just going in. Because unlike most problems you're used to, you do need to have an x and a y coordinate here to find your gradient. We get 4 over 3. So when x is 1, y is 3, the gradient's going to be 4 over 3. So then we just find the equation of the line. Plug that in. And then we're just going to rearrange this. So times both sides by 3, expand the bracket out. Just because of how little room we have. It's a long problem, as I did say. We end up getting this when we start to expand and rearrange things. I want to leave it like that for reasons I'll explain shortly. So that's what happens when x is 1 and y is 3. But also when x is 1, y can be minus 1. Okay, so if we sub in x equals 1, y equals 1 into our dy by dx, that will just become 2 over 3. Okay, so just substituted in x is 1, y is minus 1 there. And then I'm going to plug that into y minus y1 equals m times x minus x1. Okay, so just subbing in the x1 as 1, y1 as minus 1. You can use y equals mx plus c if you prefer. And then we rearrange that, and we get 2x minus 3y equals positive 5. So you've got these two tangents. Okay, so you've got something that looks a bit like this. Okay, this is a terrible diagram, but hopefully you get the idea. So you've got these two tangents. It will look a bit different to this. Plug it on GeoGebra as I did to double check and see how it looks. So if these two tangents are going to meet at a point. So what we've done is we've found the equations of both of the tangents, and now we just want to see where they intersect. So to do that, we just want to solve these two equations simultaneously now. So if I just do equation 1, take away equation 2, I get that 2x equals minus 10. So x equals minus 5. sub minus 5 back into either one of the equations to get y equals minus 5. And the answer is that they meet at minus 5, minus 5. Okay? They're not all that long. I promise they're not all that long this week. Just that one is maybe going a bit further. I just kept adding to it. Right. Question 3 then. State the range of values for which cos squared is concave in the interval between 0 and pi. Okay, so concave then. Concave means that the second derivative is negative. Okay, to be concave, the second derivative has to be negative. So let's go and find that second derivative. Now, to be fair, you did on paper 1 differentiate something sine squared. So maybe differentiating something like that might not come up again, but still, take the steps using the chain rule to differentiate. There's no reason why it couldn't come up twice, maybe. So your dy by dx is just minus 2 sine x cos x. So that's your first derivative. Now we want to differentiate that again. So you could technically, you've got function times function. You could use product rule, but why not make life a little bit easier? Let's just call that 2 sine x cos x. Whenever I see a sine x and a cos x next to each other, I always start to think, those alarm bells ring of, 2 sine x cos x is sine 2x. Can that help me? And it will here. So you're going to differentiate minus sine 2x. So this will be finding our second derivative. That's going to be minus 2 cos 2x. So if it's concave, as I mentioned at the start, if it's concave, the second derivative is going to be negative. So we know that minus 2 cos 2x is less than 0. So I'm going to look for where cos 2x, now just be really careful here, where cos 2x is greater than 0. Don't forget, if you divide by negative, you're going to need to change the direction of that inequality sign. Okay? Did that catch you out? Okay, if you did, don't worry. Learn from it. Okay, learn from those mistakes. But yeah, just remember, divide by the negative, change the direction of the inequality sign. Okay, so we're going to see where cos 2x is greater than 0. So if I'm plotting a cos 2x graph, all my x values have been halved. Okay, so with cos x, you'd have roots of pi over 2 and 3 pi over 2. But because it's cos 2x, those roots have been halved. Okay, so it's a stretch parallel to the x-axis of a half, of scale factor a half. So that's what's happened here. So rather than this going from 0 to 2 pi, this is only going from 0 to pi. And rather than your roots being pi over 2 and 3 pi over 2, they've now halved. They're just pi over 4 and 3 pi over 4. So from our sketch, you can solve this as well if you like, but I think it's better to do it by the sketch because there's multiple places where this is occurring. So I'm looking for where cos 2x is greater than 0. So you can see there it's above the x-axis when it's between 0 and pi over 4. But also, if you're between 3 pi over 4 and pi, it's also above the x-axis here as well. Oh, sorry, actually, there we go, greater than or equal to as well there. I'll explain that then. So, now it does depend on the definition in the Edexcel textbook. Does say that it's concave, it's less than or equal to 0. The exam board, as I mentioned in the previous video, they say that you can just, as long as you're consistent, say it's just less than or equal to. The reason why, though, here, sorry, I should also do it here as well. When x is 0, it's clearly positive. When x is pi, it's clearly positive. But when it's 3 pi over 4 and when it's pi over 4, x is 0. So that's where the second derivative is going to just equal 0 rather than be less than 0 there. Okay, so just explain the last little bit there for that bit. Right, on to some integration then. So we'll start off with something relatively straightforward to begin with, just a kind of reminder of some integration by parts. Again, didn't come up on paper 1, so it's quite likely to come up on paper 2, unless it comes up on paper 3 as it did last year with some stats. Okay, and I'm going to do, the next video is going to be looking at some calculus for stats and mechanics, okay, because we're not actually done with calculus after paper 2. So for this, when we do integration by parts, we need to call one function u and the other one dv by dx, okay, not u and v like product rule, u and dv by dx for integration by parts, okay. We're going to call the ux because I can easily differentiate that to get 1. And later I'm going to have to times that du by dx by v. So the fact that that's 1, 1's really easy to work with. So I'm going to call ux, differentiate it to get 1. dv by dx is e to the 2x. So when I integrate that, well, you times by the reciprocal of the coefficient of the power there. So if you were differentiating e to the kx, you times by k. If you're integrating e to the kx, u times by 1 over k. Right then, so we plug that into the integration by parts formula. That is in your formula book, so please check that out. U times v we do first, which is going to be a half x e to the 2x. And then we take away the integral of du by dx times by v. So 1 times a half e to the 2x, just be a half e to the 2x there. So I don't have to do anything else with the first term there because there's no integral sign. And I just need to integrate a half e to the 2x. So we keep the e to the 2x as it is. And then we're going to divide by 2. So a half times a half is a quarter. And the all-important plus c there at the end. Okay, there is another problem that's quite long. It's this question 5. So we've got here, I wanted to do some, I've tried to merge quite a lot of things all in one question here, yet again, thinking things that didn't come up on paper 1. There was no integration as a limit here, so when you see this sigma, we did one the other week, where you see this sigma and this limit, it might look really confusing. It basically just means integrate this between 3 and 6. Okay, that's all this means. Okay, it just means we want to integrate between 3 and 6 here. So that's what the problem is. Okay, just need to be aware that actually this is a alternative way we can write it. Okay, all to do with kind of how this all comes about, integration, which we haven't really got the time to go into in this video, but you know, is something worth checking out. So firstly, I will say as a little disclaimer, if you do further maths, you might spot some other ways to do this, okay, using the formula in your formula book, okay, so you might find some ways to kind of rewrite this and use some of those formulae, but I'm going to just approach this from completely a A-level maths perspective here. Now, what we have is an improper fraction. Okay, so we've got 16x squared on top and we've got 4x squared minus 9 on the bottom of our fraction here. So if the degree of the polynomials is the same or it's more on the numerator compared to the denominator, it's an improper fraction. So what we're going to need to do is we're going to need to do some division first. So what I'm going to need to do is, you might do the traditional long division method, but I would just be thinking, well, I've got to times something by 4x squared minus 9 to get me 16x squared. Well, that has to be 4. But I'd have to do 4 times the minus 9 to get me minus 36. So I know that if I do 16x squared divided by 4x squared minus 9, that's going to give me 4. But if I times that out, I get an unwanted minus 36. Okay, if I do 4 times 4x squared minus 9, I get an unwanted minus 36. So I'm going to need to, we have this remainder of 36 left over here. Okay, so why am I writing like this? Well, I'm just trying to make it easier for me to integrate, because at the moment I'm looking at that thinking that's just too difficult to be able to integrate. So what we're going to need to do next is think about how we could split up the 36 over 4x squared minus 9. Okay, yeah, again, if you do further maths, I imagine you've got some quicker ways of doing this. But yeah, again, I'm going to take it from an A-level perspective. Now we're going to use some partial fractions to break up that 36 over 4x squared minus 9. Yeah, again, I don't think any partial fractions were on paper 1. So what we notice is that the 4x squared minus 9, you can factorize that. Yeah, again, something when you see things in the form ax squared minus b squared, try and think about the difference of two squares there. So you've got 4x squared minus 9, that's going to be 2x minus 3 and 2x plus 3. So then I'm going to just times both sides by 2x minus 3, 2x plus 3. So we get 36 equals a times 2x plus 3. Those 2x minus 3s have cancelled. And then b times 2x minus 3. Those 2x plus 3s have cancelled. And then you sub in the x equals minus 3 over 2. Because that will eliminate the a. So we get 36 equals minus 6b. So b is minus 6. And if you sub in x equals 3 over 2, that will eliminate the b, because you'll just get a 0 in the bracket there. And then we get 36 equals 6a. So a will equal 6. So what we are trying to integrate is 4 plus 6 over 2x minus 3 minus 6 over 2x plus 3. So integrate the 4, that becomes 4x. Now, when we've got something in the form, some constant on top and ax plus b on the bottom, we want to try natural logarithm as our answer here. But if it's natural log of 2x minus 3, there's just not enough room to show how to check this. But if you want to check that, if you differentiate natural log of 2x minus 3, you can check it with the chain rule if you're not sure, you'll end up with a 2 on the top. Okay, so if you differentiate natural log of 2x minus 3, you get 2 over 2x minus 3. So we want a 6 there, so we're going to need to times that by 3 when we do that. Similar for the next one, we're going to try natural log of 2x plus 3, but if you differentiate natural log of 2x plus 3, you get 2 over 2x plus 3, so therefore we need to times that by a 3. Okay, no need for plus c here because this is a definite integral, so those c's would just end up cancelling anyway. So then we're going to sub in the 6 first, so sub the 6 into there. 4 times 6 is 24. 2 times 6 minus 3 is 9, so we've got 3 times natural log of 9. And then 2 times 6 plus 3 is 13, so you've got 3 natural log of 15. Then we're going to sub in the 3. So 4 times 3, 12. 2 times 3 minus 3 is 3. And then 2 times 3 plus 3 is 9. Okay, so then we've got that. So let's start tidying this up a little bit. 24 minus 12 is 12. 3 natural log of 9 minus 3 natural log of 9 natural log of 9, minus natural log of 9, that's hard to say quickly. 3 natural log of 9 minus 3 natural log of 9 is going to give us 6 natural log of 9, minus that 3 ln 15, and then minus the 3 natural log of 3. Now, we need to give this in the form a plus b natural log of 3 plus c natural log of 5. Okay, questions might often ask you to do this. Let's use a bit of laws of logs to sort this out. Now, first, I would look at that natural log of 9. There's going to be a lot of different ways you can do this last bit of the way, but this is just a particular way you could do it. So, natural log of 9 is the same as saying 3 squared, natural log of 3 squared. Okay, so 9 is the same as 3 squared. So what I could do is, if it's 3 squared, I can bring that power down, so multiply by it. 6 times 2 gives 12. So 6 natural log of 9 is the same as 12 natural log of 3. So I'm trying to just get them all in terms of 3s and 5s here, in terms of your natural logs. Now, natural log of 15, what I can notice is that 15 is 3 times 5. So I can rewrite 15 as natural log of 3 plus natural log of 5. Okay, using my first law of logs, log A plus log B is log AB, but just using that in reverse. And I've just got that minus natural log of 3. That's fine because it's already a natural log of 3. So we have 12 natural log of 3 minus 3 natural log of 3 minus another 3 natural log of 3. So we've got 6 of those altogether. And then I would take away 3 lots of natural log of 5. Okay, and then that would be my answer. Okay, so I've got it in that form. Now I will say, in the exam situation, if you're really, if you're spending too long trying to get it in a particular form, okay, it would usually be worth kind of 2 marks at the end. Don't spend 20 minutes trying to chase 2 marks, okay? Move on to something else, get some confidence with some other questions, and then if you've got time at the end, have another go at it, okay? But there you go. That's the answer for that one. That's hopefully quite, includes quite a few topics in that, not just integration as a sum there. So remember, if you see that sigma, think integration. Well, see the sigma and the limit notation, think integration. But also some partial fractions, some division, some differentiating fractions that turn into natural logs, log manipulation, lots of stuff there for you to have a go at. Right, final one then. We're going to look at so we started with some parametric differentiation, which seems like a long time ago now, but we're going to finish with some parametric integration. Now, for parametric integration, we use the fact that if we was just integrating our Cartesian curve as normal, we'd differentiate y, which is some function of x, and we'd integrate that with respect to x. Okay, but because we've got these equations defined parametrically, okay, what I'm going to do is divide and times by dt. What that means is that, well, if y is a function of t, I can find dx by dt, which will also be a function of t, and then I can integrate that result with respect to t. So let's just tidy that up a little bit. So if you have y times dx by dt, and you integrate that with respect to t, that's how we can integrate these parametric equations. Okay, yet again, it's going to be much simpler than finding your Cartesian curve and then just integrating that instead. Okay, so that's not in your formula book, so you do need to remember it, by the way. Okay, so y we already have. We're going to need to find dx by dt. Okay, so dx by dt, differentiate tan, it's in the formula book, this one, you just get sec squared. So now we can just plug this in. We've got y, which is sine squared, times dx by dt, which is sec squared. Now, what I also need to do is have new limits. So our limits are no longer going to be these x limits as 0 and 1. I now want t limits instead. So what I'm going to need to do is look at x equals tan t, and look at what happens when x is 0 and when x is 1. So when x is 0, so tan t equals 0. Well, t is just going to be 0. And when tan t is 1, t is going to be pi over 4. Okay? Usually, by the way, a question like this in exam would have a diagram that accompanies this. Okay? But my limits are going to be not 1 and 0, but now going to be pi over 4 and 0. So I'm going to integrate sine squared sec squared, but actually we can make this a lot nicer for ourselves by simply recognising that sec squared is just the same as 1 over cos squared. So this becomes sine squared over cos squared, but sine over cos is tan, so sine squared over cos squared, that's going to be tan squared. But still, there's no rule in the formula book for integrating tan squared. But there is a rule in the formula book for integrating sec squared. And we've learnt from trig identities that tan squared can be written as sec squared minus 1. Okay? So that, just remember, you can just derive that from the, sine squared plus cos squared equals 1, divide both sides by cos squared and rearrange, and you'll get there, and you'll see there that tan squared is sec squared minus 1. Okay? Have a go at that. Pause this and have a go at that if you want to just prove that for yourselves. Okay, so I did that because in the formula book you get that when you integrate sec squared you get tan. So integrating sec squared we get tan. Integrate the 1 with respect to t, but that's just t, we pi over 4, and then just sub the pi over 4 in, so tan of pi over 4, that's going to give us 1. Please make sure we're in radians, okay, always in radians when we're doing calculus, and then the t, just putting the pi over 4 there. Okay, we can keep it exact because that's what we've been asked to do, and often in the exams you will be asked to leave it exact rather than as a decimal. When you sub in the lower limit of 0, well, actually both of those terms go to 0. So 1 minus pi over 4 is just our solution here. Okay. So if you've got any questions, please ask. So I'm going to be back next week. I'm going to try and get it out a little bit earlier, but time's always it's quite difficult to find the time to do these recordings. So try and get it out as soon as possible. But try and do a special kind of applied version. Okay, because there is some calculus, obviously not as much as you'll see in the pure, but especially with mechanics, you will have the, your acceleration, velocity, displacement, variable acceleration questions, vector calculus questions, and potentially can even get a little bit of calculus, as we have seen a few papers with stats as well. So look forward to seeing that. But hopefully you've gone all right with those. If you've got questions, let me know. Happy calculus, everyone.